Hi, this is Daniel, and I'm trying to build my own little database in Java. If you are interested in the source code, you can download it on GitHub. The link is in the description. New videos will be released on Sunday every week. At least I hope so. As you can see, I already created a little project in here. We do have the package structure of DE, then hobby, and MoiSql, and there is a package called tree in this structure. And within this tree, we have 4 classes. One abstract class, but 4 classes. Yeah. The main data structure we are using to implement the table is called a B plus tree. A B plus tree is a regular B tree, and a B tree is actually a balanced tree. That's why it's called a B tree. It means the left side and the right side, they always have the same depth of its leaves. We are using such a data structure so we can quickly find elements within the tree. And if we are using like numbers, we take the ID of a row of the database, and we're looking for this certain ID in this B tree, and attached to this ID is then the row of the table. So the tree is a representation of a table of the database. In the database, of course, we do have more than one table, so we have more than one B tree in a database. So let's have a closer look at B trees and how they are working. I found a little website that actually shows B trees really nice. Here I just dragged it in, and let's have a look. This website shows quite neatly how B trees work. So we go there to the insert field, type in 100, click on insert, and you see the first node is created. Now let's insert another value. Which one should we take? Let's go with 85 and insert that, and then you can see something strange. Actually, node can contain more than just one value. So let's see what happens if we add another value, in this case 75, and you see it splits up. The 85 is now the root node, and the 75 is a leaf to the left, and the 100 and the 85 are to the right side. So if you're wondering why there's 85 twice in this constellation, B plus trees, the real values just can be stored on the leaves. The parents are just there as navigational help, as so to speak. So in our case, it means if it's smaller than 85, it's to the child on the left side. If it's 85 or higher, it's the child not on the right side. Let that sink in real quick. So you have this 85, and if it's smaller, you have a children node on the left, and if it's the same, or if the value is the same than 85 or higher, it's the child on the right side. So you probably wonder how this continues. So let's try it and add another value. So let's take 90. Suddenly we have 3 leaf nodes. One's the 75, one's the 85, and the third one is the 1900 node. Suddenly, the root node has 3 children. That's what this max degree on the right side or in the center up there means. A node can have 3 children. And one node can have the number of maximum children minus 1 values. So here we have the degree is 3, we have 3 children, and the maximum number of elements we can save in one of those nodes is 2. The children are put together in the following way. So the rules are pretty straightforward. If it's smaller, it's the left side node. If it's bigger, it's the right side node. And if it's in the middle, it's the center child. Let's add another value. Let's take 80. So 80 is smaller than 85, so it's added to the left node. Nothing really fancy happened there. Let's add another small value like 81 or something, yeah, and let's see what happens now. A whole new level is created, and the leaves are again on the same level, now on level 2, but the 80 and the 90 are now the values are now the first level, and the root level, the 85, is a single node. What I did not mention before is that each leaf has a pointer or reference to the next leaf. This comes in very, very handy if you want to have ranges. So when you have like the range from 75 to like everything smaller than 85, you just you just go to the 75 node and then walk to the 80 node and then the 81 node, and then you see that the 85 is bigger, and so on. And so you can traverse the whole list simply, but you can select single elements quickly with this kind of data structure. So let's have a little look at the POM file where the project is defined. You can already see I did some programming, so I'm already there at version 002. Yes, I need a hobby. That's why that's the group ID. We're using Java 21. We're using UTF-8 as text encoding, and we are using JUnit 5 in the version 5.14. Then there is logbag as a logger, and the rest of it is just testing dependencies. I wanted to have as few dependencies as possible in this project. So the only one you could argue is is this one, this dependencies. That's not really necessary, but I just like it. Now let's look at the code. Before we look at the code, I already defined a logbag configuration file. It's there in the resources. It's just a console appender, and I define the root level. This is really the easiest logger you can probably write, and well, it gives me a logging, or gives us a logging throughout the whole project. So when I started programming with this abstract class, abstract because there is an abstract method in it. The class is called node, and a node contains basically just a list, an array list to be specific, of type integer. I called this list keys, and in this list there are the numbers you saw before on the in those nodes. That's where they're stored. It's just a simple list. In addition to this array list, we have a reference to another node. I called it parent, and if this is the child, so you can have a reference to the parent node. And there is this abstract class, abstract method is leaf, and all classes inheriting from this node will have to implement them. One of those classes is the internal node. It is a node, and it's like it inherits. It's also a node, but it has a list of children as well, a list of nodes that are the children. These remember when we had the website, and we are implementing the isLeave method, and since it's an internal node, we always return false. It's not that hard actually. So, and those internal nodes are just internal, and then we have the leaves. They are also extending from node. These are nodes as well. Here we have a pointer to a reference to the next leaf node, and the that's the arrows where you can run through. You remember that, and the method isLeave always returns true. That is the basic data structure. And now we have to implement this whole thing. So I call it a BP tree, which is stands for B plus tree. And I looked around and got some different algorithms and implemented them. I hope they are correct, but I'm not completely sure. So in the beginning, we do not implement data yet. So those rows of tables, that's not there. It's just the keys. It's nothing else. So the leaves have no data rows of the table inside. First of all, we have a logger. Always nice to have. Then we can give it the magnitude, which is on the website it's called degree, sometimes it's called order, sometimes it's called magnitude. That's the value that defines how many children one node can have. And we have the root node, a reference there, so we have a starting point. Here we do have the constructor. It takes an integer value called magnitude and sets the magnitude. The magnitude has to be bigger than 2, otherwise B plus trees do not function. Furthermore, we're setting furthermore we give an illegal argument exception if you're smaller than 3, and then we're setting the magnitude in this class. Then we're setting the root node, and then we are saying, hey, so some kind of output that we just created B plus tree. So inserting a key into a B plus tree, first of all, we need to find the leaf where this where we want to insert this key. So first of all, we have to find the leaf. We start traversing the tree, starting with the root and the key, and that's the parameters for this method. Not null is one of those nice annotations, so you don't have to have null checks all the time. And now we're actually walking through this the tree. So while if it's not a leaf, we're gonna go through the children. Oh yeah, the list of children. Get the right um, iterator. Like in our case, it's de. Add it up until we have the right, uh, yeah, the right child. Yeah, and since twice, yeah, while loop, it can operate there quite efficiently, and then you get you traverse down to the leaf, and then return this node as a leaf node. It's yeah, look at it. It's in the beginning it's a little bit yeah strange, but after a while it comes out. It yeah, it's okay. So you can see I already did write a little bit more. So then we need to uh, insert. Now we have the leaf, and then we want to insert this this key at the right position. Again, we are doing it with a while loop, and we are looking just if the key is smaller, what's there, yeah. Then we add one to I, and then we finally have the right counter, and then yeah, edit it this place. Just have a look at it. The code is at GitHub, yeah, and that's the main part actually for inserting, yeah. And however, if not is becomes too big, we have to split the leaf up. Remember when it splits there? And max keys is just like a little method I wrote, just a little helper, nothing fancy. It just gives yeah, magnitude -1. Yeah, it's hard coded, but yeah, it's easier to see. So now we have to split the leaf. Splitting the leaf is actually not that hard. First, you take the middle of it. Here I said mid, yeah, and then you copy the left side to the old one and the right side to the new one. After that, you insert it into the parent, because you know the new value has to be in the parent as well. Where the heck is the... Where is it? Where is it? Where is it? Well, I have it somewhere. It is there. Let me... Where? Well, it's not that important. We also have implemented a delete function. Delete is the same thing, actually. Might be a little bit more complicated, but it's actually just a copying of indexes to left and right. So if you want to look at it. Here is a test, a little little test I wrote, and let's run it. And yes, of course, there are no assertion, and oh, okay, that was just like this one. Here we do if the magnitude didn't work, and then we have some inserts and deletes, and you can see that the root is 100, and then level 1, level 2, level 1. It's just like the tree is from left to right, and it actually looks okay to me. I'm actually pretty happy with it. Maybe there are some more bugs, but no, we'll see. So let me say thank you to all of you. I hope the video is not too long. I tried to keep it short, and especially with those trees, it's like a hassle for like the iterations going like iterator and then while loops, and you just count up 1 and 2. Well, I thought that would be pretty much very, very boring. And please don't forget that that was my first video, and I am not a video guy. I am actually a Java programmer or programmer. So please forgive me if the video is not as good as you thought. I tried to make it better. Leave leave a comment there, and yeah. So thank you very much for listening. Thank you very much for watching. And if you have any suggestions, yeah, leave a comment. And I see you next week. Next week we are talking about data types. So enjoy your Sunday. Have a nice week. See you next Sunday. Bye bye.